Research priorities. The next 18 months of autonomous coding. AI-powered coding assistants are already transforming software development. By late 2025, tools like GitHub Copilot and AI chatbots are being used daily by most developers. And even non-programmers can prototype code with simple prompts. Google's CEO notes that this trend, often called vibe coding, is making programming more approachable for non-technical staff. However, real-world deployments have exposed important gaps. AI-generated code often contains subtle bugs, fails on complex projects, and raises accountability and policy issues. To move from lab demos to reliable production systems, we need focused research on 4 fronts: reliability, long-horizon planning, verifiability, and socio-technical governance. Below, we outline key open problems and propose research agendas, benchmarks, and collaborations to tackle them. Reliability and code quality. A major issue is basic reliability. Code written by AI assistants still contains significantly more errors than human code. For example, an analysis of 470 GitHub pull requests found AI-written PRs had about 1.7x more issues than human-written ones. On average, AI PRs triggered about 10.8 issues, logic bugs, naming or formatting problems, security flaws, etc., versus 6.5 for human PRs. Notably, the AI-authored code had a heavier tail of severe bugs. Logic errors and security vulnerability appeared nearly twice as often as in human code. In practice, teams using AI tools have reported surprises: code that looks correct in isolation but fails integration or carries hidden flaws. Indeed, a comprehensive survey of code generation tools observes that existing benchmarks do not capture the kinds of failure modes seen in production: hallucinated API calls, inconsistent naming, or subtle logic errors that slip past unit tests. In short, AI can generate working code snippets, but those snippets are often not ready for production. Developer experience echoes this mistrust. A large SonarSource survey found that while 72% of engineers use AI tools daily to write up to 42% of code, a staggering 96% admit they do not fully trust the AI output. Yet fewer than half of teams always review AI-generated code before committing. This gap, high usage but low trust, leads to what experts call verification debt. Without better reliability, organizations risk introducing hard-to-catch bugs and technical debt whenever they adopt AI coding shortcuts. Research agenda. We need systematic study of error patterns in AI code and new methods to mitigate them. Ideas include automated AI proofing, integrating static analyzers or secondary models that scan AI output for common mistakes, similar to a second reviewer. Better LLM training objectives could focus on stability. For example, training on buggy versus clean code examples to teach the model to prefer safer solutions. Researchers should analyze which types of code, algorithms, I/O, security critical, trip up AI's internal heuristics, and develop specialized defenses. For instance, early work has flagged that AI tools overuse risky shortcuts, hard-coded passwords, inefficient loops, etc. We must codify these failure modes. Educational solutions can help too. As community guidelines stress, AI tools can only assist, humans must verify. To encourage this, future tools could auto-generate warnings or even refuse to handle tasks without human approval. Benchmarking should shift, moving beyond "does this code compile?" to "how many subtle issues remain?" For example, code review AI models are emerging that specifically measure bug detection performance. A community effort to produce a public dataset of real AI versus human code changes with annotated defects, akin to CodeRabbit's PR study, would let researchers track progress in reliability. Long horizon planning and maintenance AI code generators excel at small, self-contained tasks, but large projects expose their limits. Real software evolves over time, with changing requirements, multiple files, and architectural decisions to manage. Surveys note that generating correct isolated functions differs qualitatively from maintaining coherent architectural decisions across a large codebase. In practice, even state-of-the-art models struggle with multi-step, multi-file tasks. 2 recent benchmarks highlight this gap. Roadmap Bench, May 2026, evaluates long-horizon upgrades on real open-source projects. Each task gives the agent a base version of a project and a list of features to implement, with 3,700 lines change across 50-plus files. Even Claude Opus 4.7, one of the strongest models, solved only 39% of tasks, and other models fell as low as 5%. By contrast, simple one-shot bug fixes see near-perfect AI performance. Roadmap Bench authors conclude that long-horizon software development remains a largely unsolved problem. Slop Code Bench 2026 examines iterative development. Agents were given a task and formed code. Then over 20 rounds, the task specification changes, forcing code to evolve. The result? Even though all intermediate versions passed existing tests, the AI-generated codebases became 2.2x more verbose and much harder to maintain than human-maintained code. In fact, none of the top models solved the full sequence, 5% by the final checkpoint. This shows that small design mistakes accumulate under AI assistance, hindering future modifications. These findings suggest research focus on planning and decomposition. AI systems should not just write code per prompt, but plan multi-step strategies. One emerging idea is plan and execute. Let the model first outline a design or sequence of steps, then generate code for each step. In fact, analyses of coding agents, Claude Code, GitHub Copilot, etc., find that separating planning from execution and exposing the plan to the user dramatically improves performance on complex tasks. Research should develop new architectures. For example, nested agents, where a manager LLM breaks a big problem into subtasks for worker LLMs. Long-term memory mechanisms are also needed. Future models should remember code generated earlier in a session, even beyond the context window. Benchmarks. The community should define benchmarks that reflect real dev work. Going beyond Roadmap Bench, we need tasks spanning multiple languages and integration challenges, front-end, back-end, databases, etc. Simulated team projects would test how AI and humans collaborate over releases. Borrowing ideas from software engineering, benchmarks could measure not just correctness, but maintainability. How easy is it to add a new feature? Performance. Does AI code degrade as it evolves? And integration. Does it fit existing style conventions? For example, benchmarks could start with an existing codebase and ask the agent to implement a series of feature requests or refactorings with periodic tests. Over the next 18 months, creating such open challenges, perhaps via academic industrial contests, will guide research into multi-stage coding. Verifiability and formal interfaces. As AI assistants attempt more critical tasks, ensuring correctness becomes essential. Verifiability means linking code to precise specifications or test suites, so we can be confident it does what we want. In classic engineering, one writes a formal spec or thorough tests before coding. How do we bring this mindset to AI-driven coding? One opportunity is closed-loop generation. Recent work proposes that in AI-generated code, its docstring and any formal annotations should be checked for consistency. For instance, the Clover approach automatically generates formal specs using languages like Daphne alongside code, and then uses proof tools to reject inconsistent solutions. In early tests, this detected all incorrect programs on a textbook-level dataset. Similarly, AutoACSL uses static analysis to prompt an LLM to write precise function contracts, pre-post conditions, and then verifies them with from a C. By feeding back unsatisfied conditions, it dramatically improved the percentage of provably correct code. These examples show that integrating formal methods at the code generation step can turn an uncontrolled AI guess into a verified program. Apart from formal math, we also need better interfaces between informal specs, tests, and code. Today, it is common to describe a function in English and hope the AI does the right thing. But we should also have the AI generate or ask for test cases, type annotations, and design comments. For example, a prompt could first ask the model to describe the algorithm or invariance in natural language or pseudocode, and only then to code it. Or we could use contract-first development, write unit tests or property tests that the AI must satisfy. Rough sketches of these ideas have shown promise. Even generating a few example-based tests can steer the model away from trivial solutions. Benchmarks. New benchmarks should include formal check problems. For example, we could add tasks where the correctness is verified by a theorem prover or symbolic checker, not just unit tests. Datasets of user stories with LTL, TLA+, or alloy specs and corresponding code would be valuable. In education, competitions like the TLA+ Model Check Challenge show that specifying is hard. One study found current LLMs achieve only about 8% semantic correctness on straightforward TLA+ specs. Open source projects might release specification languages more widely, a sort of coding affidavit. Standardized formats, YAML, JSON for API specs or data schemas could be leveraged by AI to align code with intended behavior. Socio-technical governance and trust. Finally, autonomous coding raises human and policy issues. Who is responsible for AI code? How do we ensure security, copyright compliance, and accountability? Several organizations have begun addressing this, but open questions remain. Developer practices. As mentioned, industry surveys show a trust gap. Developers know they should review AI output, but often skip it if it's easier, leading to unmanaged risk. In response, major projects have set explicit rules. For instance, the Open Infra Foundation permits AI assistance only if commits are labeled with an assisted by or generated by tag. Google's Chromium project similarly requires that authors fully understand any AI-suggested code, or else lose commit privileges. Mozilla's Firefox policy states bluntly, AI can assist, but responsibility always stays with the human behind the change. Even the NumPy project warns that you must be able to explain any code submitted. These policies underscore that technical tools alone are insufficient. We also need clear workflows and culture. Regulation and standards. On a broader scale, governments and standards bodies are catching up. The EU is finalizing a code of practice for general-purpose AI, which will require transparency and safety measures from AI model providers. While this is not specific to coding, it signals tighter scrutiny on training data licenses and model explainability, both highly relevant if your code assistant pulled from copyrighted code. Similarly, ISO and IEEE have begun AI standards for governance and ethics, though only a few directly address code generation. The AI Act (EU) and upcoming US guidelines will likely influence how companies vet AI code internally. Collaboration needed. Closing these socio-technical gaps will require joint efforts. Academia can study how AI tools affect team productivity, vulnerability discovery, and licensing. Industry can share anonymized data on real AI-related incidents. Standard bodies like W3C, IEEE can incorporate coding scenarios into ethical AI guidelines. For example, workshops could bring together SAT-EL, software assurance experts, with ML folks to define evaluation criteria for AI code safety. Guidelines could evolve into standards, e.g., IEEE 8201 AI-assisted software process, giving organizations a common framework. Over the next 18 months, building consensus on best practices through white papers, consortia, or open-source policy templates will help teams adopt these tools responsibly. Research and benchmarks agenda. To summarize, we suggest the following concrete steps for the research community. Augmented benchmarks. Develop a suite of benchmarks that mimic real software projects. For example, multi-module frameworks, web apps, APIs, embedded systems, where the AI must implement new features and then maintain them. Include evolving specs, simulating changing requirements. Measure not just test pass rates, but code complexity, readability, security metrics, and review workload. Work with industry to source real bug fix histories and feature requests as benchmark tasks. Error taxonomy study. Systematically categorize the kinds of bugs AI introduces. CodeRabbit's report gave an initial breakdown, logic errors, naming issues, etc. A larger academic study could gather PR data and classify AI versus human errors. This would guide new model losses, e.g., extra weight on security and automated detectors, tools that flag typically AI gone wrong patterns. Planning and multi-agent research. Explore architectures like planner-executor agents. Investigate how to give AI systems some form of memory across sessions or enforce hierarchical planning. Collaborate with existing work in agentic AI and robotics, repurposing multi-step reasoning methods for code. Formal methods integration. Invest in research like Clover and AutoACSL that tie in program synthesis and proofs. Encourage formal methods researchers to partner with NLP/ML groups. For instance, academic competitions could pair LLM code assistants with provers on shared tasks. Create competitions for AI-generated proofs or contract inference. Governance frameworks. Social science studies on team practices and liability. For example, run developer studies, give teams AI tools, and observe how they review and debug. Legal research on IP. As one blog notes, the Copilot copyright problem, unlicensed code, is an open issue. Standards bodies should draft clear guidelines around data licensing and attribution for AI code. Tooling and interfaces. Final, build tool prototypes that demonstrate best practices. An example, an AI coding IDE plugin that automatically runs static analysis or tests on any AI-generated code and warns the user. Or a CLI that labels all AI-assisted sections in a codebase. Encourage open-source projects to adopt AI-used badges or commit message conventions. These informal standards can later be formalized. By defining community benchmarks and holding multi-institution challenges, like an AI coding hackathon, to meet certain security or maintainability targets, we can track progress. Think of it like how ImageNet drove vision. We need a shared ImageNet for code that reflects real development. Early efforts, RaidMap Bench, Slop Code Bench, Sigma Bench, point the way, but next we should scale them and make them widely available. Formal interfaces, specs, tests, and code. A central opportunity is tighter integration of specifications and tests into the coding loop. In traditional development, a spec describes what the code should do, and tests check it. AI tools can help connect these. For example, a promising practice is spec-driven generation. Write a possibly informal specification first, then prompt the AI to code it. Even better, one could co-develop the spec with the AI. For instance, ask the assistant, generate unit tests for this requirement. Then use those tests to validate the code. This creates a formal interface. The natural language spec, the tests it implies, and the code form a tight triangle. On the research side, one could define a standard format for specs, e.g. a YAML or JSON schema describing functionality, and require AI systems to consume it. Efforts like TLA+, Alloy, or BDD-style tools, Cucumber, might be integrated. Imagine telling the AI, please generate code that satisfies this TLA+ model. Although LLMs today are not great at writing TLA+ from scratch, combining a human-written abstract spec with AI-augmented code generation is worth exploring. The goal is to make it easy for teams to produce a runnable specification, even if informal, that the AI respects. Formal tests could then be auto-generated. Recent work shows GPT models can produce property-based tests given a description of function behavior. More ambitiously, we can create formal specification templates. For cloud deployments or security-critical code, define a template, e.g., user authentication flow with fields. The AI fills in the template and generates code. A validator checks the contract. By providing these interfaces, we transform coding from a black box into a more controlled pipeline. Initiatives like the AI tools for TLA+ or LLM to spec translation, ongoing in some research groups, are early examples. In practice, even partial adoption, asking AI to output comments or type signatures, can improve correctness. As a first step for developers, incorporate simple spec test loops now. For instance, if using ChatGPT, start your session by writing, "We want a function that does X, write tests first." Then ask it to generate the implementation. Even without fancy formal tools, this enforces a discipline where AI always produces code with an accompanying check. Over time, this habit can become formalized into standards for AI coding. Collaboration, academia, industry, and standards. Achieving these goals requires broad collaboration. Academia can contribute by creating and sharing data and benchmarks, and by publishing rigorous evaluations. Universities should partner with companies to get real code bases for testing. Research labs can hold open challenges, with prizes, on tasks like long-term code quality or verified code generation. Industry must provide feedback loops. Firms deploying AI coding tools should anonymously share bug statistics, contributor experiences, and feature requests. Tech companies can also fund AI for coding workshops or tracks at conferences, like ICSE, FSE. They can open source parts of their policies, as Google did with Chromium's AI policy, so others can learn. Standards bodies, IEEE, ISO, W3C, etc., should incorporate coding into existing AI ethics and safety standards. For example, ISO's ongoing work on AI governance, ISO IEC 38507, and AI lifecycle, ISO IEC 5338, could explicitly call out code generation. The W3C has an ethical principles draft for WebML. This could be extended with a section on programming use. A lightweight code of practice for AI-reliant development teams should emerge, much like secure development standards, e.g. OWASP, exist for security. In short, the path forward is socio-technical. Just as open-source communities formed coding standards and review cultures, the emerging field of AI coding needs shared norms. Joint roadmaps, e.g. industry consortia on AI code safety and transparency, publishing benchmarks and failure cases, will bring everyone onto the same page. Who benefits and how to get started? Crucially, AI-assisted coding is not just for expert developers. These tools can democratize programming. Beginners and subject matter experts can use AI to jumpstart projects they'd never have time to code by hand. For example, a marketing analyst could ask an AI to write a data reporting script instead of learning Python from scratch. An artist could prototype an app UI by sketching a prompt. In each case, the AI lowers the barrier to creation. To get started with these tools, follow the same agile, iterative workflow that professional teams use. Define a clear goal or specification. Begin by stating what you want in concrete terms. This could be a natural language description of a feature or a simple sketch of steps. For programmers, even a list of bullet points or user stories can serve. Use an AI assistant to draft code. Run an AI coding tool. Many are available, online chatbots or IDE extensions, and ask it to implement the spec. For example, you might type, create a Python function that reads a CSV and plots the data points. The AI will generate a first version. Verify and refine. Crucially, take the AI's output and test it. If it's code, run it in your environment. Write or auto-generate some simple tests. Does it give correct results on basic cases? If something fails, it often will on the first try, give feedback to the AI. For example, highlight the failing case and ask it to fix the code. Many tools allow iterative prompting or multi-turn editing. Ask for explanations and documentation. Use the AI to produce doc strings or comments after the fact. This helps you, the new coder, understand what was done. You can also ask the AI to point out potential issues or suggest improvements. Gradually increase complexity. Once simple scripts work, you can attempt a small project, e.g. a to-do app, a data analysis pipeline. Divide the project into pieces. Ask the AI for each component, database schema, front-end, business logic, one at a time. Treat it like pair programming, where the AI is your junior partner. First next step, pick a beginner-friendly AI coding tool and try a small experiment. For instance, use an interface like GPT-4 with code capabilities or a free extension in your code editor. Give it a trivial task. Sort a list, make a graph, hello world web page. Then read the code. Even without coding experience, look at the structure. Run it and note any errors. Then repeat, refine your prompt, maybe add more detail or constraints, and regenerate. Over time, you'll learn how to communicate effectively with the tool and how to guide it toward correct solutions. New coders should keep in mind, AI is a powerful assistant, not an oracle. Always check its work and use it as a learning opportunity. Write your own tests for the AI's code, run them, and ask follow-up questions until you're confident. This check then trust habit is how everyone, novice or expert, should safely build with AI. Conclusion: the rise of autonomous coding tools is a watershed moment. But to fully reap the benefits, we must confront the open problems unveiled by early deployments. In reliability, we see that code assistants make more mistakes than humans. So research must focus on error detection and robust generation. In planning, we see agents falter on long multi-step projects. So we need new architectures and benchmarks for complex workflows. In verifiability, we recognize that we need formal spec and testing support built into the AI coding process itself. And on governance, companies and regulators are scrambling to set rules so that AI code is transparent, safe, and accountable. Over the next 18 months, progress in each of these areas will be essential. By building rigorous benchmarks, from project planning challenges to inspection of AI-induced bugs, integrating formal methods into AI coding pipelines, and forging collaborations across disciplines, we can close the gap between flashy demos and real-world reliability. The vision is clear: an AI coding ecosystem where even beginners can safely create software, and where the code that AI generates is as trustworthy as human-crafted code. Meeting this vision will require shaping both the technology and the practices around it. With focused research and broad community effort, the next generation of AI tools can truly unlock coding for everyone, starting today. All links to sources are available in the text version of this article. You can find the full article at easycoding.tools.blog. Thanks for listening. For more practical AI coding guides, tool comparisons, and resources for builders, visit easycoding.tools. And if it's easier to remember, just go to aibuilds.it. It redirects to easycoding.tools.